Section 4.9 we'll talk about conformations of alkanes. And this is really getting down to what the shapes of the different structures are that we've been drawing. And a conformation is just a different arrangement of atoms caused by rotation of single bonds. So there are two common ways that we try to draw this and draw 3D structures in 2D. So we're going to use ethane as an example. So I've got CH3, CH3. So one way to do it is to draw it sort of like we draw a sawhorse. So here's my back carbon, and here's a bond to my front carbon. So these are both carbons. And I can draw my back hydrogens going up, and then down towards the back. Sort of like legs of a sawhorse. That's why this is called a sawhorse conformation. In my front one, I can do the same thing. Here's my hydrogen coming up, and I can draw my other two hydrogens going down. One coming down forward and one going down towards the back. Now that's only one possible conformation. We can rotate one of these. So let's keep the back one the same and rotate the front one. So if I draw my back one again, I can rotate the front so that now rather than having one hydrogen going straight up, I've got hydrogens going up to this side and up to this side, and one going straight down at the bottom. So these are both ethane. They're both the same molecule, but they're different conformations of it. And in the first conformation, this hydrogen and this hydrogen, one is directly in front of the other, so we call those eclipsed. While in the other conformation, there is no hydrogen directly in front of this one. It's rotated to the side of it from that, so we call these ones staggered. Now the sawhorse view isn't used very much. Quite often though, what we will use is what's called a Newman projection. So let's first do a Newman projection of the eclipsed structure that's already drawn there. And in a Newman projection, we say that we're looking down a bond. So I'm going to start and say that I'm looking down from C1 to C2 of ethane. Whatever is in the front is a small dot, and whatever is in the back is a larger circle. So we look at this front carbon, which is the small dot, and we say, okay, what does it have on it besides the bond to the other carbon that's going in the back, which ends up being the large dot? And so one thing it has is a hydrogen going straight up, and then it has a hydrogen coming down to the right, and it has a hydrogen coming down to the left. Then I can look at the back carbon, and that has a hydrogen going up, and it has a hydrogen coming down to the right, and it has a hydrogen going down to the left. Now, you'll notice that I didn't draw these in the exact same spots, even though they're eclipsing each other, so that we can see the different atoms. But they're actually in the exact same positions, just one atom behind. So now let's do the exact same thing for the staggered one. So I would encourage you to pause the video, and you try and see if you can draw the Newman projection for the staggered structure, and then come back and see how well you did. Alright, so if I start at the front carbon, I've got a hydrogen coming straight down. I've got one coming up to the left, and I've got one going back to the right. Those are out of the front carbon. Then I move to the back carbon, which is the bigger circle. I've got one going straight up. I've got one coming down to the right and one going down to the left. So these are Newman projections, eclipsed and staggered. And this will be our first chance to see another one of our 5 areas, and that is sterics. And sterics is a really fancy word for just saying that big things don't want to be near each other. And any chance that things they'll try to get so that the larger groups or any groups will be further apart than they would be together. So with that idea that things would rather be farther apart than together, would it seem better to have the structure eclipsed or better to have it staggered? Hopefully it's apparent right away that staggered is going to be lower energy.